Okay, so we'll begin with this. As I said to you yesterday, we're moving on to a new section. It's the polar form of a complex number. Okay? Now, it's actually something really straightforward. It's a no-brainer. Again, we need to have done trigonometry, obviously, before we do this, or it might prove to be a little bit difficult to understand. But imagine that this is our Argand diagram here. So obviously, this here is the real axis, and this here is the imaginary axis. Okay? And then let's imagine that I pick just some random complex number. Okay? So I'm not confusing you, I'm going to pick a random complex number in the first quadrant. But the fact that it's in the first quadrant doesn't really matter a whole lot. Is that okay? So this is our complex number z, which we'll just say it's a plus bi, or a plus ib, whatever way you want to write it. Okay? Now, an alternative way of viewing this situation is to draw a line from here out to here, call this r. Okay, remember yesterday I used r at some stage. Okay, so call that r. And then the way we measured the angle before, remember from the radius at that point in trigonometry around to the positive x-axis. In other words, the angle from here to here. Okay, we call that theta. Right? So if that angle there is theta, and I drop a line down along there, simple trigonometry, if I call this A and this B, for obvious reasons, simple trigonometry is going to dictate that cos of theta equals adjacent over hypotenuse, so A over R. Is that okay? And if I cross multiply, that means that A equals R cos theta. Okay, so A equals R cos theta. Now, similarly, I could say that sine of theta equals B over R. And again, if I cross multiply, I'm going to get B equals R sine theta. Is that okay? So B equals R sine theta. So that means then that Z equals A plus IB. So Z equals R cos theta plus IR sine theta. Is that okay everywhere? So all I'm doing is just putting in R cos theta instead of A and R sine theta instead of B. Simple stuff. Now what I'm going to do is I'm going to take out the common R. So Z equals R into cos theta plus I sine theta. Is that okay? So generally what the examiner would say is, here's a complex number, can you go and write it in the form R into cos theta plus I sine theta? They wouldn't actually use the term polar form. I'm throwing it in there, but they wouldn't actually use it. Okay, they'd say express it in the form R into cos theta plus I sine theta. Okay? Well, it's called, as I said, polar form of a complex number. Now, for simplicity, as I said, I picked a complex number in the first quadrant. But I could have just as easily picked complex number in any other quadrant, and all I have to do is move theta like we did before. Okay? Now also, just from a point of view of terminology, 2 or 3 years ago they asked, one of the simplest questions they ever asked, but very few people got it right. They asked, find the argument of z. Okay, the argument of z. Theta is the argument of z. Argument is just a posh name for that angle. Is that okay? It's some people call this modulus argument form. Okay, modulus is R and the argument is theta. Is that okay? So if they ask it this year, what's arg z? It just means get the angle. Okay, that's all it means. The only thing I would ask you is that when you're getting arg z, will you please quote it in radians? Okay? Now, I have to say, predominantly I'm going to use degrees when I'm talking about theta. But if they specifically say write down arg z, just do that bit in radians. Is that okay? Degrees are okay everywhere else, just not for arg z. Okay, that needs to be between 0 and 2 pi. Is that alright? Okay? Now, as I said, this is a piece of cake. Okay, it's simple. So, let's do an example. So, our example is express. By the way, if this comes up, it is very, very likely that one of the questions I do today is going to be the question. Okay? Because they're not really going to vary the numbers too much. Because they want to end up with 45 or 30 or 60 or 120 or 135 or 150. Do you know what I'm saying? They'll want to end up with a standard angle. Okay? So chances are what we do today will come up. Okay? So express will say minus 1 plus I in the form r into cos theta plus I sine theta. Okay? So I express minus 1 plus I in that form. When you're doing this, you always begin by drawing an Argand diagram. Never ever do this without drawing a diagram. Okay? It's wrong to do it without a diagram. So here's our real axis, here's our imaginary axis. Okay? You actually don't need to go to the hassle of scaling it out. Okay? You don't need to scale it out. Minus 1 plus I presume everybody would agree, is somewhere over here in this quadrant. Yes? Now, how would you get to that place? Well, to get to that place, I presume you'd all agree, you go back 1 and up 1. Yes? Back 1, up 1. Then R is the hypotenuse there that I've just drawn. So this is R. Now, is everybody in the room clear on the fact that there's theta? Is that okay? So would you agree that arg z in this question is going to be an angle between 90 and 180, quoted in radians? Is that okay? So all we got to do here is find out what r is, find out what theta is. Okay, now to get theta, I'm going to first of all find alpha. Okay? Would you agree with this? Tan of alpha is opposite over adjacent, which is 1 over 1, which is 1. So what's alpha? Well, alpha has to be 45 degrees. Okay, alpha must be 45 degrees. Now what's the relationship between theta and alpha? Theta is going to be 180 minus 45, which is 135 degrees. Okay, now isn't that simple? Now, as a matter of interest, I didn't ask it, but what's arg z? Isn't it 135 divided by 180 multiplied by pi? Because pi is 180 degrees. Pi radians is 180 degrees. 45 goes into 135 3 times, 180 4 times, so arg z will be 3 pi over 4. Is that okay? Just if they ask that little bit there. Okay, as I said, it's simple. Hopefully they will ask it. Okay, but from here on I'm going to ignore the radians and keep dealing in degrees. Okay, so theta is 135 degrees. That's that part sorted. Now I need to work out r. Now r is the modulus of the complex number, which is the modulus of minus 1 plus I. And remember from yesterday's class that modulus, it's the square root of the real part squared plus the imaginary part squared. And what were the two things I told you to remember? There is no mention of I, it's just the coefficient of I that we put in. Okay, and the sign in the middle is always plus. Is that okay? So, quite obviously, I think you'd agree that r is going to be the square root of 2. Is that okay? So r is root 2. So that means then that minus 1 plus I have to write it in the form r into cos theta plus I sine theta. Okay? which is root 2 into cos of 135 plus I sine 135. Is that totally clear with everybody? Okay, so it's a really, really simple job to do. Okay, there's nothing at all to it. We all okay? Now, we're going to be doing this loads and loads and loads of times today. So what I'm going to do first of all is I'm going to move away for a minute. I'm going to talk about the theorem of the Moivre. Okay, I'm going to talk about the theorem of the Moivre. I'm going to basically prove it. And then we're going to come back to modulus argument form and link the two. Is that okay? Now, first of all, I promised you yesterday that this was going to make our lives much, much easier for manipulating complex numbers. Okay? So before I prove the theorem of the Moivre, I need to prove a simple fact. Okay? So let's prove this. It's an important proof. If Z1 equals R1 into cos theta 1 plus I sine theta 1, and Z2 is equal to R2 into cos theta 2 plus I sine theta 2, then number 1, Z1 Z2 equals R1 R2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Is that okay? So that's the first thing I'm going to prove. And then I'm going to ask you to prove this one for homework. It's a little bit harder, so it's a bit of a challenge for you. Z1 divided by Z2 is R1 over R2 into cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Is that okay? Now, if you look at that very quickly, you can see the simplicity in it. Like if you look at this thing here, when I'm multiplying two complex numbers in modulus argument form, all I got to do is multiply the two r's together and add the angles. Okay, how simple is that? You just add the angles together. You remember yesterday when I was going around adding 45 degrees every time like the hands of a clock going backwards? It just gives me, that was what was giving me the ability to do that yesterday. Okay, I knew I was just adding a particular angle every time I went around. And if multiplication means add the angles, theta 1 plus theta 2, it kind of makes sense as well that division should mean subtract. Is that okay? So these are two very useful formulas. Now, as I said, the second one I'm going to ask you to do for homework. Once I've shown you how to do the first one, you'll cop on how to do the second one. Okay, it's quite simple. The only reason I'm only proving the first one today is because I need it. I need the first one for the Moivres theorem. Is that okay? I need it. So, here's our proof of part 1. Now, I'll do part 2 in the next class, okay? I just want you to give it a go for homework. Right, so Z1, Z2. I think everybody would be pretty okay if I wrote this down. It's R1, R2 into cos theta 1 plus I sine theta 1 multiplied by cos theta 2 plus I sine theta 2. Remember, when you're multiplying numbers, order doesn't matter, does it? So the fact that I've moved the two r's over side by side is irrelevant. Okay, it's simple, isn't it? So we're all totally okay with that? Now all I got to do is multiply out the brackets and tidy up the mess that's going to appear. So here's what we have. R1, R2. Let's just write that down and get it out of the way. Cos theta 1, cos theta 2. So I've multiplied that bit by that bit. Now I'm going to multiply this bit by this bit. I suppose, I'm just using my head here. I've noticed that when I multiply I by I, I'm going to get I squared. So that's going to be another real bit, isn't it? So I'm just multiplying it in such a way that I have the real bits together and the imaginary bits together. Okay? So what's I sine theta 1 multiplied by I sine theta 2? It's I squared sine theta 1 sine theta 2. Is that okay? Now, if I multiply the first part here by the last part in the second bracket, I'm going to get an imaginary bit, haven't I? And would you agree I'll also get an imaginary bit if I multiply the last part of the first bracket by the first part of the second? Yes? So is it okay if I do this? Plus I, let's multiply the first part of the first bracket by the last part of the second. That's going to be cos theta 1 sine theta 2. Okay? And now multiply the second part of the first bracket by the first part of the second bracket. And I'm going to get plus sine theta 1 cos theta 2. Again, what I've done is I've taken the I outside. Okay? Now what's I squared? Everywhere we see I squared, what do we put in instead of it? Minus 1. Okay? So I'm going to be putting in a minus 1 instead of that guy. So that means the next line is going to be R1, R2 into cos theta 1, cos theta 2 minus sine theta 1, sine theta 2 plus I into cos theta 1, sine theta 2 plus sine theta 1 cos theta 2. Is that okay all around? Alright, so I've just multiplied out two brackets. I haven't done anything fancy here. Okay, just multiplied out two brackets. Now I want you to think about this. Think trigonometry. Cos A cos B minus sine A sine B. What's that? It's one of our formulas from trigonometry. It's cos A plus B. Is that alright? So would you agree then that this first part here, just put in theta 1 instead of A and theta 2 instead of B, it's actually the cos of theta 1 plus theta 2. Okay? And the second part over here, cos A sine B plus sine A cos B, what's that? It's sine A plus B. Is that okay? So I'm just borrowing those formulas from trigonometry again. Alright? So now we're done, aren't we? That means then that Z1, Z2 equals R1, R2 into cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And there we are, we're done. So that means then to multiply two complex numbers in modulus argument form, all I've got to do is multiply the r's and add the angles. Is that okay? That's all. Just multiply the r's, add the angles. Division, subtract the r's, divide the r's, I should say, and subtract the angles. Okay? And that's what you're going to prove for homework. Now, don't make a big deal out of it. When you're dividing those two complex numbers, Z1 divided by Z2, all you got to do is multiply top and bottom by the conjugate of the bottom line, and then look out for cos A minus B and sin A minus B appearing. Is that okay? Also, when you do it, you're going to notice that cos squared plus sine squared appears a lot on the bottom. And what's cos squared A plus sine squared A? 1. So cos squared theta 1 plus sine squared theta 1 would be 1. Cos squared theta 2 plus sine squared theta 2 would be 1. Is that okay? So just look out for those kind of things when you see the bottom. Is that okay? Right. So now let's look on and have a think about the Moivres theorem. So if you have two complex numbers that are in modulus argument form, what do? You multiply the r's and you add the angles. Okay? And here's the Moivres theorem, or the version of it that we prove anyway. Cos theta plus I sine theta to the power of n equals cos n theta plus I sine n theta for n an element of n. Is that okay? So we prove a kind of a diluted version of it for natural numbers. Okay? However, it does work for integers and rational numbers as well, and real numbers. Is that okay? But we only prove it for natural numbers. Well, where have we ever seen questions like this before? We have to go back a long way, don't we? When did we see it before? Induction. Is that okay? When we were doing proof by induction. So remember, proof by induction is a 4-step process, isn't it? What are the steps? Prove true for n equals 1. Assume true for n equals k. Prove true for n equals k plus 1. And then draw your conclusions. Is that okay? It's a 4-step process. Prove true n equals 1. Assume true n equals k. Prove true n equals k plus 1. And then make a conclusion. And obviously our conclusion hopefully is going to be the Moivres theorem is true. Okay, that's the conclusion we want to end up with. So step 1. I need to prove it's true for n equals 1. Now, cos theta plus I sine theta to the power of 1. Well, isn't that just cos theta plus I sine theta? Isn't it? As to the power of 1 is irrelevant, isn't it? But sure, isn't that the same as saying cos 1 theta plus I sine 1 theta, isn't it? So it doesn't matter whether the 1 is out here or the 1 is multiplied by theta, it's the same thing, isn't it? So what's the verdict? Is it true for n equals 1? You bet it is. Okay, so therefore it is true for n equals 1. Okay? Now, second thing. What do I do now? I assume it's true for n equals k. Alright? In other words, some random domino in the middle. Remember we talked about a line of dominoes. Okay? So I assume it's true for n equals k. So what exactly am I assuming here? I'm assuming that cos theta plus I sine theta to the power of k is equal to the cos of k theta plus I sine k theta. We all happy with that? Is that clear with everybody? Now you can obviously be 100% sure that we have not seen the last of that, have we? The assumption is something that you definitely will be using again. Is that okay? You see, our proof in step 3, proving true for n equals 1, is going to be based on the foundation of knowing that the assumption is true. Is that okay? Or hoping that it's true. Is that alright? So we're on to step 3, which is prove true for n equals k plus 1. So if domino k falls, we have to prove that that's going to knock over the next domino. Is that okay? So what are we trying to prove? I.e., I'm trying to prove that cos theta plus I sine theta to the power of k plus 1 equals the cos of k plus 1 multiplied by theta plus I sine k plus 1 multiplied by theta. Is that okay? That's what I'm trying to prove. Now, by the way, at the moment, would you agree this is just wishful thinking? I haven't proved anything yet. I need to prove that. So what I'm going to try to do here is I'm going to try to start off with the left-hand side and end up with the right-hand side. Is that okay? And I know for certain that I'm going to be using that assumption again, that little bit there at the top of the screen. Okay? I have to end up using that. So here's the actual proof. So I'm starting off with the left. Cos theta plus I sine theta to the power of k plus 1. Now remember, what you and me have to do is we have to find a way of bringing in the assumption. So how could I use cos theta plus I sine theta to the power of k? Absolutely. So isn't cos theta plus I sine theta to the power of k plus 1 the same thing as cos theta plus I sine theta to the power of k multiplied by cos theta plus I sine theta? Are we agreed? But you see, my assumption tells me that the first bit here is not all my assumption. That part. So those two bits in yellow are the same. So that means what I can do is I can put in cos k theta plus I sine k theta instead of the yellow bit, multiplied by cos theta plus I sine theta. And I need to say there, by my assumption. Is that okay? Without the assumption, I would not have any legal right to put that in there. Is that okay? Now, do you notice anything now? What are we doing now? Aren't we multiplying two complex numbers in modulus argument form, aren't we? When you're multiplying two complex numbers in modulus argument form, don't you just multiply the r's and add the angles? Now, in this case, r is just 1, isn't it? There are no r's. It's just like there's a 1 outside the bracket here. Okay? So we don't need to worry about the r bit. So all you and me have got to do here is add those angles. So that's cos of k theta plus I sine k theta plus theta. Which are now we're done, aren't we? Because all I got to do now is go cos k plus 1 multiplied by theta. In other words, take out that common theta and do the same for the imaginary part. And there we go. So what exactly do I write down now? Thus, the statement is true for n equals k plus 1, provided it is true for n equals k. Is that alright? So it's true for n equals k plus 1, provided it's true for n equals k. But remember, it did work for 1, didn't it? You see, what we've effectively done is to prove that if it's true for one number, it's true for the next number. Now we know it's true for 1, so then it must be true for 2. Which are now we know it's true for 2, so it must be true for 3. You understand me? But now it's true for 3, so it must be true for 4, and we could spend the day here talking like that. Okay? So it's true for all n. So thus the statement is true for n equals k plus 1, provided it's true for n equals k. Since it was true for n equals k plus 1, for n equals 1, it will also be true for n equals 2, 3, 4, etc., and so on for all n an element of n. Is that okay? So therefore the Moivres theorem works. And this, remember, this part down here, it's kind of like the fourth step in the proof. It's your conclusion, it's important, you have to word it well, you have to be careful you get all the information in there. Okay? So the statement must be true for n equals k plus 1 because it was true for n equals k. But it was true for n equals 1, so it must also be true for 2 and 3 and 4, etc., and so on, for all n an element of n. So the moral of the story is this: cos theta plus I sine theta to the power of n equals cos n theta plus I sine n theta for n an element of n. Is that okay? Now I've proved it there for n an element of n. But it will, it will also be true for other number systems as well, for integers, for real numbers, and so on. Is that okay? It will also be true for other number systems. Sorry about that. So there we go, the Moivres theorem. Okay? Everybody happy? Now the question is, how do we actually use it? Okay, so let's do some interesting examples. This is kind of part one. It's usually a part one, part two question. Okay, part one is get this into the correct form. So express, we'll say -1 minus root 3i in the form r into cos theta plus I sine theta. Okay? And then part two, express -1 minus root 3i to the power of 10 in its simplest form. So obviously for part two, that's where the Moivres theorem comes in, isn't it? Okay, writing it in its simplest form, putting it to the power of 10. Now, if I had two options, option one, multiply -1 minus root 3i by -1 minus root 3i 10 times to work this out. And option two, use the Moivres theorem. I'd use the Moivres theorem every time. Is that okay? Most definitely. So anyway, let's begin with part one. And obviously that starts with a picture. So there's my Argand diagram. This is the real axis. This is the imaginary axis. It's okay to write RE and IM, by the way. That's perfectly okay. Now, where would -1 minus root 3i be? Where would it be? Which quadrant? Isn't it somewhere off down here? Okay. Now, quite obviously, the length of that is r. Okay? Now, to get to there, I would have to go back 1 and down root 3, correct? So back 1, down root 3. Let's call this angle in here alpha. Now, I'm not really interested in alpha. I'm much more interested in theta. Now, where does theta start and finish? Isn't that guy theta? Would you agree with that? So once I found out what alpha is, how am I going to find out what theta is? Add it to 180, exactly. Okay? Add it to 180. So first of all, tan of alpha equals root 3 over 1, which is just root 3. Well, can you remember what that makes alpha equal to? It's obviously not 45, so is it 30 or 60? It's 60. Is that okay? So alpha is 60 degrees. So therefore, what's theta? It's 240 degrees, because theta is obviously 180 plus alpha. Is that okay? Now again, so we keep thinking along these lines, just in case it's asked, what about arg z? Isn't it 240 over 180 multiplied by pi? Isn't it? Which is 4 pi over 3. 60 goes into 240 4 times, and 60 goes into 183 times, so 4 over 3. Is everybody okay with that? So if, as I said before, if they ask you for arg z, just please quote it in radians. Okay? Right, now r. R is obviously the modulus of z, which is the modulus of -1 minus root 3 I. Okay? So that's going to be the square root of minus 1 squared plus minus root 3 squared. Notice no mention of I, and the sign in the middle is always plus. Now that's the square root of 1 plus 3, which is the square root of 4. So then obviously r equals the square root of 2. Is that okay? Sorry, the square root of 4, which is 2. We all right? So that means then that if I want to express it in the form r into cos theta plus I sine theta, I have minus 1 minus root 3i equals r into cos theta plus I sine theta, which is going to be 2 into cos of 240 plus I sine 240. Is that okay? And there we go. So that's part 1 out of the way. So minus 1 minus root 3i is equal to that mess there. Okay? Now in part 2, what we're asked to do is now work out minus 1 minus root 3i to the power of 10. Okay? Now if we were working it out the other way, multiplying minus 1 by root 3i repeatedly, we'd probably be at around about minus 1 minus root 3i cubed at the moment. Okay? We'd probably be around about there if we were lucky. Now for part 2, they want to know what's minus 1 minus root 3i to the power of 10. Well, isn't this to the power of 10 the same thing as this thing here to the power of 10? Yes? So isn't that the same as 2 to the power of 10 multiplied by the cos of 240 plus I sine 240 to the power of 10. Is that okay? Now 2 to the power of 10, let's just leave that as it is. Okay, let's not bother writing down, it's 1024 or something like that, but let's not complicate things by writing that down. If I was to apply the Moivres theorem here, what would happen? The Moivres theorem tells me that I can bring the 10 down inside the brackets and multiply it by the angle. So what's 10 multiplied by 240? 2400. So that's cos of 2400 plus I sine 2400 degrees. So that's obviously using the Moivre. Okay? Using the Moivres theorem. Are we all totally clear on what I'm saying here? Now, the next part that I'm going to do is actually quite simple, but just be careful with it. I'm going to go 2400 divided by 360. You see, 2400 degrees means I've gone around the circle a hell of a lot of times, doesn't it? Okay? So what I want you to do is simplify it for me as a fraction. So it's probably about 6 and 3/4 or something. What's 2400 divided by 360? 6 and 2/3. Every time I go around in circles, would you agree I end up back where I started? Would you agree with that? I end up exactly back where I started. So what I've done here is 2400 degrees is the same as going around a circle 6 times and then doing 2/3 of a circle. So interestingly, I'm not interested in the 6 at all. I'm only interested in the bit that's left over, the 2/3. Is that okay? So 2400 is the same as 2/3 of 360, 2/3 of a circle. And this is just a pure coincidence, by the way, because 2/3 of 360 just turns out to be 240 degrees. But that's pure coincidence. Is that okay? It could have turned out to be anything. All right? The fact that it turned out to be the 240 that we already had is a fluke. Okay? So don't take that as the norm. Okay? In fact, I wish it didn't happen. Okay? I'd be much happier if I got 150 or something like that. Okay? So it need not have been 240. So that means then that that's 2 to the power of 10 cost of 2,400 we've just worked out is the same as the cost of 240 plus I sine 240. Now, would you agree that we are in a quadrant where both costs and sine are negative? Yes? We're in the third quadrant. How do we get into the third quadrant? We add our reference angle to 180. What would you add to 180 that would give you 240? 60. So the cost of 240 is the same as minus the cost of 60. And the sine of 240 is the same as minus the sine of 60. Is that okay? So this is good practice for trigonometry really, isn't it? Do you all understand why they're minus? We're in tan's quadrant now, aren't we? We're not in the quadrant of sine or cos. So that's 2 to the power of 10 into minus a half minus root 3 over 2i. Because cos of 60 is a half, the sine of 60 is root 3 over 2. Okay? Now, do you notice anything? Isn't there a 2 on the bottom here and here? Couldn't I pull that 2 outside? Okay, I could pull that 2 outside. And what's 2 to the power of 10 divided by 2? 2 to the power of 9 into minus 1 minus root 3i. Is that okay? Now, I can go back now. Like, I didn't know exactly how this was going to turn out because it was a question that I made up off the top of my head. Okay? But here's what the examiner would probably say. I said simplify minus 1 minus root 3i to the power of 10. They would probably say express your answer in the form 2 to the power of n into a plus b root 3i for n an element of n and a and b an element of z. Is that okay? That's the way they probably would have phrased it. Instead of saying simplify like I did, they would say express minus 1 minus root 3i to the power of 10, the top of the page, in the form 2 to the power of n into a plus b root 3i for n an element of n and a and b an element of z, using the Moivres theorem. Is that okay? That's probably the way they would have phrased it. So does everybody entirely understand what just happened there? We're all okay? All right, that's brilliant.